Hey everyone, welcome back to linear algebra. This will be lecture 6 of the course. And in this section we're going to add on to what we discussed in the previous section where we were talking through Gaussian elimination, and we introduced the idea of row reduction, row operations, etc. So we're going to go a little further in this one and introduce Gauss-Jordan row reduction, and then ultimately the reduced row echelon form, which will become important for the things to follow. So let's go ahead and jump into it. We'll call this section 2.2, and this will be Gauss-Jordan row reduction and reduced row echelon form, frequently abbreviated RREF. Okay, so in the previous section, we discussed Gaussian elimination, the method, and from that, we were able to, taking that idea and combining it with the idea of an augmented matrix, we could come up with an augmented matrix for a given linear system and then systematically reduce the matrix until the matrix had a particular form. And so what we would see with our, is kind of the end result of that process would be matrices that had a particular form, like the following: 1, 3, -7, 3, 0, 1, 5, 2, 0, 0, 1, 8. Right, so remember this is an augmented matrix, right? So we had our coefficient matrix over here together with our scalar matrix over here. And so what we've done is we went through and we identified our pivots. We eliminated the zeros below the pivots. And this produced a matrix that looks something like this, for example. And using this, we can back substitute to figure out what the value of x1, x2, and 3 are. Okay. Another example would be something like this, a slightly bigger matrix: 1, 2, 17, 9, 6, 0, 0, 1, 3, 9, 0, 0, 0, 1, -2, and then maybe an all 0 row here. And again, this is a augmented matrix, right? And this is a very likely this would very likely be the result of, doing the Gaussian elimination process that we just discussed. Now, in each case, the form is sort of a stair-stepping down of the pivots, like so. Right, so here you've got a pivot row or pivot column. It steps down, then you got another one, and it kind of looks like that, right? So this sort of stair-step structure with the pivots is kind of key. Matrices in this form are said to be in row echelon form. So matrices in this form are in row, let's make that capital, echelon form. Okay, they're in row echelon form. Now, we can extend the Gaussian elimination. One obvious thing we could do would be to extend the Gaussian elimination to also deal with the values above the pivots. So, for example, in this matrix here, Gaussian elimination says, okay, just clear out, create zeros beneath the pivots. Well, we could also come in and target these entries as well, right, and turn those into zeros. In this matrix, we could come in and easily target that 17 and the 9 and 3 because they're above the pivots, and we could turn those into zeros as well. And so this is a very simple and obvious extension of the Gaussian elimination, and this is what's meant by Gauss-Jordan row reduction. So the simple extension of Gaussian elimination that zeroes out also, we'll say also zeroes out the entries above the pivots is called, and this is the Gauss, obviously it's in base, it's half of it is the Gaussian elimination, and then the other part of it is the Gauss-Jordan. The Gauss-Jordan row reduction. All right, so this is basically just Gaussian elimination, but additionally, we're going to zero out everything above the pivots, right? And you can imagine that's going to basically use the exact same mechanism as before, right? Except now we're going to target things above the pivots. Okay, so let's do an example. Let's do an example using Gauss-Jordan elimination. Let's go ahead and just kind of work it end to end here and make sure this is clear. Okay, so I'm gonna, given the following system, let's go ahead and use Gauss-Jordan elimination. And so I'm gonna actually write the system out just because we'll come back and actually solve it. I want to see how this all ties together. So let's say the system is this. So 3x1 okay, so here's our system. All right, so 2x1 plus x2 plus 3x3 equals 16 is the first equation. 3x1 plus 2x2 plus x4 equals 16 is the second equation. And then 2x1 plus 12x3 minus 5x4 equals 5 is the third equation. So we can plug this into an augmented matrix. And we have 2, 1, 3, 0, 16, and then 3, 2, 0, 1, 16, and then 2, 0, 12, negative 5, 5. Okay, so our augmented matrix would look like this. Again, these are this is the coefficient matrix on the left-hand side and the scalar matrix on the right-hand side. Okay. And so we can go through this and we can easily use the Gaussian elimination, but then in addition add on the goal of eliminating the above the pivots as well. Okay, so we'll start by multiplying row 1 by 1/2. Okay, and so row 2 and 3 are unaffected, so let's just write those in real quick. And then what do we have for our row 1? Well, it's going to be 1 and then 1/2, 3/2, 0, and 8. Okay, so just multiplying that original row 1 by 1/2. All right. Now the next task, remember, in Gaussian elimination is to say, let's get rid of the 3 and the 2, convert those both to zeros. And so we can do that by multiplying row 1 by -3 and adding it to row 2. And that will deal with this guy, this 3. And then to get rid of the 2, to turn the 2 into a 0, we're going to have to multiply row 1 by -2 and multiply and then add that result to row 3. Right? So this is the notation I use just to keep track of what I'm doing. Right, but whatever notation you have in mind, that stick with it if it's working for you. So 1, 1/2, 3/2, 0, and 8. That's our row 1 unaffected. And so let's go through and see what happens with row 2. So -3 times 1 is -3, plus 3 is 0. -3 times 1/2 is -3/2, plus 2 is 1/2. Okay. And then -3/2 times 3/2 is -9/2, plus 0 is -9/2. Right? So again, I'm doing this times this plus this. -3 times 0 is 0, plus 1 is 1. And then -3 times 8 is -24, plus 16 is -8. Okay, and so that's our new row 2. Then we do the same thing with row 3. So negative 2 times 1 is negative 2, plus 2 is 0, of course. That's why we chose negative 2. Negative 2 times a half is negative 1, plus 0 is negative 1. Okay. Negative 2 times 3 halves is negative 3, plus 12 is 9. Negative 2 times 0 is 0, plus negative 5 is negative 5. Negative 2 times 8 is negative 16, plus 5 is negative 11. Okay, so that is our new row 3. Okay, and now we can get a pivot in our 2, 2 spot, right? We can see that this could easily be converted to a 1. So we're going to multiply row 2 through by 2. Okay, so again, row 1 is unchanged, and row 3 is unchanged. So let's go ahead and write all of those in. Okay, and now we'll multiply everything here by 2, and so we get a 0 and a 1 and a negative 9 and a 2 and a negative 16. Okay, very good. And now the Gaussian elimination would say let's turn the negative 1 into a 0, and so we'll do that. And to do that, it's really, you can kind of think of it as multiplying this row by 1 and then adding it to this next row. But in reality, we're really just going to add the 2 together, aren't we? Right? So 1 times 1 is 1, 1 times negative 9. So this is unchanged, add it to the next row, and that becomes your new row 3. In addition, because we're interested in doing Gauss-Jordan row reduction, we need to turn this 1/2 into a 0 as well. Right? So how are we going to do that? Well, we're going to multiply this row by negative 1/2, and then we're going to add it to the top row. Now notice here, the nice thing about this is that as we go to up to the, as we start doing row operations that are basing row 2 into row 3, this pivot is not going to be affected because everything below the pivot is already a 0. Okay, so that's a nice fact here, right? So if you're working from left to right, and your work that you've already done should be safe and should remain unchanged, because you should have all 0 entries in your pivot rows as you move to the right. Okay, so that's a nice thing. This wouldn't quite work if that weren't the case. Okay, so in this case, our row 2 is going to remain unchanged. So let's write that in. So 0, 1, negative 9, 2, and negative 16. Okay, and we'll just start by doing the bottom, row 3 first, because it's just a little bit easier. So 0, and then 1 minus 1 is 0. Negative 9 plus 9 is 0. 2 minus 5 gives me a negative 3, and then this is going to be negative 27. So that's negative 16 times 1 is negative 16, plus negative 11 is negative 27. Okay, so that gets me this. All right, so now I've got the 0 here. And then I need to go and multiply everything by negative 1/2 and add to the top. So negative 1/2 times 0 is 0, plus 1 is 1. Negative 1/2 times 1 is negative 1/2, plus 1/2 is 0. Okay, and then negative 1/2 times negative 9 is 9/2, plus 3/2 is 12/2, right? So this becomes a 6. Okay, negative 1/2 times 2 is negative 1, and then negative 1 plus 0 is negative 1. Okay, then negative 1/2 times negative 16 is 8. 8 plus 8 is 16. Okay, so I get to this. Very good. And now what comes next? Well, we have a pivot here. We have a pivot here. And we can see now that it's not possible to get a pivot here, right? No, there's no row operation which can turn this into a 1. right? So our next pivot will be this guy. Okay, and so the way to do that is to just multiply by negative 1/3. Okay, so row 1 and row 2 will be unaffected here. So 1, 0, 6, negative 1, 16, 0, 1, negative 9, 2, negative 16. And then this will be 0, 0, 0, 1, and then negative 27 times negative 1/3 is a 9. Okay, what's left to do? Well, if this were just Gaussian elimination, we would be done, but we're interested in Gauss-Jordan row reduction, right? So we do have a pivot here, and we've got some non-zero entries above it, so these need to be converted to zeros. Okay, and so the way to do that is to take negative 2 times row 3, add it to row 2, and let that be your new row 2, and also take so this negative 1, so we could multiply and do kind of the same trick of 1 times row 3 added to row 1 is your new row 1. Okay, so pretty simple calculation here. So 0, 0, 0, 1, 9 is stay the same this time. And now let's go ahead and tackle row 2. So that'll be 0, 1, negative 9, those are going to be unchanged because you'll be adding 0 to them. So 0, 1, negative 9. Now here you're going to get 1 times negative 2 plus 2 is a 0. And then 9 times negative 2 is negative 18 plus negative 16. That actually gets me negative 34. Okay, so that's my new row 2. Now what about row 1? Well, again, you're going to have 1, 0, 6 are going to stay the same because of these zeros. Okay, and then it's going to be 1 times 1 is 1 plus negative 1 is 0. And then 1 times 9 is 9 plus 16 is 25. Okay, and so this is the final result of Gauss-Jordan row reduction. All right, so this matrix. All right. And so notice here, not everything is zeros and ones over here. You do have these guys here that are still non-zero entries. Now, why are they non-zero entries? Because they're not in a pivot column, right? So Gauss-Jordan row reduction just says turn everything in pivot column should be either ones or zeros. The pivots are ones, everything else in the pivot column is 0. Okay, and so these are not in a pivot column, so they're kind of on their own, doing their own thing. Okay, let's convert this into back into the system notation and see what it leaves us with. So we'd have x1 plus 6x3 equals 25. That's the first equation. And then we would have x2 minus 9x3 equals negative 34. And then we would have x4 equals 9. And so this would be our system, right? If we were to take this augmented matrix, it's row reduced using Gauss-Jordan, and convert it back into the system notation. And this is what it looks like. And so kind of looking at this, we can see that x3 is our only non-pivot variable, right? So x3, if it's a non-pivot variable, that means it's an independent variable. So x3 is non-pivot, right? So x3 is an independent variable. Okay. And so we can identify the solution to the system here by simply coming in and saying, let's let x3 equal some number c, we'll say, some real number c, right? Then x2 minus 9x3 equals negative 34. Well, just plugging in c here, you get x2 minus 9c equals negative 34. And that implies that x2 is going to be equal to 9c minus 34, right? Just doing that little bit of algebra. So you've got that part. And x1 plus 6x3 equals 25, right? So again, we can just plug in c for x3. We get x1 plus 6c equals 25. And that's going to imply that x1 is equal to 25 minus 6c. Right? And so then the solution set, right? The solution set, what's the solution set? Well, it's going to be the following. 25, x1 is 25 minus 6c. X2, we see, is 9c minus 34. X3 we defined as just c. And x4 is constant at 9. Right, that was kind of the output of the system. And this is all such that c is a real number. Right, so this is going to be an example of a system that has infinitely many solutions. All right. Okay, so this system has infinitely many solutions. Okay. And this actually brings us to the idea of reduced row echelon form. Okay, this Gauss-Jordan row reduction will, taken to completion, will produce a matrix that is in reduced row echelon form. So the Gauss-Jordan row reduction will produce a matrix that is in reduced row echelon form, RREF. Okay. So we've seen some examples of RREF. Well, we just saw one example so far, actually. But let's talk through the characteristics of a matrix in reduced row echelon form. So let's define it. So a matrix is in reduced row echelon form if and only if all of the following conditions hold. Okay, so there'll be 4 conditions that need to be met. First of all, the first non-zero entry in each row is 1. Okay, so let's look at our previous matrix here as we walk through this. So here was our previous matrix. And so the first non-zero entry of each row, right, going kind of left to right, is 1, right? So here you can see the first one is 1, first one is 1, so 0, 0, 0, 1. Okay, so that's the first condition. The second condition says that each successive row, right, each successive row has its first non-zero entry in a later column. Okay, what does that mean? Well, if we look again at this example, so each successive row, so starting at the top, successive rows would be rows further down in the matrix, right? So for example, this first row has its first non-zero entry in column 1. The second row better have its first non-zero entry in a later column, and that's what you see, in fact, column 2. Row 3 has to have its first non-zero entry in a column later still, so beyond column 2, and you see that it's in fact column 4. Okay, so that's all that means. Now these first two items here sort of spell out the stair-step nature of the pivots of the matrix. Okay, so this matrix we're looking at in this example, and in fact reduced row echelon form matrices in general have a stair-step pattern. Okay, and that's what 1 and 2 establish. What about item 3? Right, condition 3. All entries above and below the first non-zero entry of each row are 0, right? So this is the Gauss-Jordan reduction piece, right? So all entries above and below the first non-zero all entries above and below the first non-zero entry of each row are 0. Okay? And that's what we saw, of course, in this example. Here's a pivot. Everything in that column besides the pivot is 0. Here's another pivot. Everything above and below is 0. Here's a column with no pivot, so that one doesn't, this condition doesn't apply. Here's a pivot. Everything above and below is 0. Okay, so that's okay. And then item 4, the last condition, is that all full rows of zeros are the final rows of the matrix. Okay, and we don't have an example of an all 0 row in our previous example, right? All of our rows had, you know, entries that were non-zero, right? But if in fact you had another row and that row did contain all zeros, then it would be at the bottom of the matrix, not somewhere near the top or in the middle. It'd be at the bottom. Okay, and if you had multiple non-zero rows, they would all be at the bottom. Okay, so those are the 4 conditions that indicate reduced row echelon form. So if all 4 of these conditions are met, then your matrix is in the RREF format. Let's see some examples of matrices in reduced row echelon form. Okay, so some examples. Let's just write a couple out. 1, 0, 0, 6, 0, 1, 0, negative 2, 0, 0, 1, 3, for example. This would be a nice system. This would be a great solution. You've got a unique solution. You can read it right off. x3 is 3, x2 is negative 2, x1 is 6. So this would be an example of RREF, right? You've got the stair-step pivots. You've got zeros above and below the pivots. You've got, and you know, we don't have a row with all zeros, but if we did, we would put it at the bottom. And so this is a perfect example. Another example would be something like this: 1, 0, 2, 0, negative 1, 0, 1, 3, 0, 4, 0, 0, 0, 1, 2, and then all zeros at the bottom. Okay, so this is going to fit the bill of reduced row echelon form as well. All of your pivots are on the diagonal, right? Everything above and below the pivots is 0, so all zeros, 0, 0, 0, zeros, more zeros. You do have a non-zero column here, but that's a non-pivot column, so that's okay. You do have an all 0 row, and it's at the bottom of the matrix. Okay, so you can see the stair step here, and you've got the zeros at the bottom. Okay, what about something like this? This matrix in reduced row echelon form, it's augmented matrix. Well, you've got the stair step stepping down like this, so that looks okay. The pivot columns, you've got zeros below here, you got zeros above and below here, and you got zeros above here. That's okay. There's no full row of zeros. You do have this lower row here where all of the coefficients, all the entries of the coefficient matrix are 0, but you have a scalar 1. This is okay, right? Because it meets the criteria. This would just be an inconsistent system, right? This would be a system with no solution, because you can't have, there's no x1, x2, x3, x4 that's going to make this that's going to satisfy its last equation. But these are all in RREF form. Okay, they're all in reduced row echelon form. Okay, so notice this again, the key things here are the staircase pattern of the pivots, non-zero, non-pivot entries only in columns without pivots, right? So here and here, here and here and here, these are okay because they're non-pivot columns. And well, you can see here, this one is going to have a unique solution, which we saw. This one will have infinite solutions because you've got a pivot, a non-pivot column, which we'll see in a second. And this is going to be no solution, right? Because you've got this equation at the bottom that will never have a solution. All right, and so this example is a nice example to work up to the following result. Okay, the following result. So I'm going to call it a theorem. Okay, I'm going to call this a theorem. And so what do we got? We've got, so let AX equals B be a system of linear equation. Okay, let AX equal B be a system of linear equations. Let C be the reduced row echelon form of, the augmented matrix AB. Then, okay, so C is basically going to be the, this entire matrix, augmented matrix, but reduced row echelon form of AB. Okay, three possibilities exist here, and so the first one, if there is a row of C having all zeros in the coefficient side of AB and a non-zero entry to the right, then AX equals B has no solution. So basically, if you get this kind of a pattern, right, where you've got a row of the matrix C where the coefficient side's all 0, but the scalar side is non-zero, then you're going to have an inconsistent system, and AX equals B will have no solution. So let's write this out. If there is a row of C having all zeros in the coefficient side of AB, right? The coefficient AB, coefficient matrix would be A, and a non-zero entry to the right, then AX equals B has no solution. Okay, so that's the first thing, right? And here's the example of it, matrix that looks like this. All right, no problem, no problem. Okay, item 2 then, right? So if here's 1, the first thing to check is, do you have a situation like this? If you do, then you have no solution. Item 2 says, if not 1, but if one of the columns of C has no non-zero pivot entry, then AX equals B has infinitely many solutions. Okay, so what is it saying? Well, first of all, we don't have the situation from 1, right? So there's no row that looks like this. But we do have one of the columns of C having no non-zero pivot entries. So something like this, right? So this doesn't have the problematic row, but it does have a column that has a non-zero pivot entry. That does not have a non-zero pivot entry, right? So this column 3 in particular has no non-zero pivot entry, right? So what that's going to imply is that I've got independent variables in the system, and that means I will have an infinite number of solutions. Okay, and so that's basically what condition 2 is describing. Okay, and then column 3, otherwise, AX equals B has a unique solution. Okay, otherwise you're going to have a situation like this, right? Which so otherwise means that we're not going to have any column with a non-pivot, right? Right, and that's going to mean you're going to have a perfect stair-step situation like this, right? Otherwise, also you're not going to have this kind of situation. You could have a perfect stair-step with a 1 here and all zeros here, but then that would fall into condition 1, right? So if that's not happening and you don't have columns without pivots, then you must have a perfect stair-step like this, which means you're going to have a unique solution. Okay? So those are sort of the 3 things that can happen when you have a matrix, an augmented matrix that's been reduced using Gauss-Jordan row reduction and is in reduced row echelon form. Okay. When you have that, these 3 possibilities emerge, and you can quickly just look at the matrix and make a determination regarding this nature of the solution space. Okay. All right. Very good. Let's move on. We're going to introduce a special kind of linear system called a homogeneous system. Okay, so a system of linear equations having matrix form AX equals 0 is called a homogeneous system. Okay, so a system of linear equations having matrix form AX equals 0 is called a homogeneous system. All right, so a couple of examples here. So maybe 2x minus 3y equals 0, negative 4x plus 6y equals 0. That's a homogeneous system. Okay. Another one would be 5x1 minus 2x2 plus 3x3 equals 0, 6x1 plus x2 minus 7x3 equals 0, and negative x1 plus 3x2 plus x3 equals 0. This is another example, 2 examples of homogeneous systems. All right. So these are 2 examples of homogeneous systems. Now, something to notice here is that when you have a homogeneous system, it's guaranteed to be consistent, right? So notice, and you can kind of think about it just by looking at these 2 examples, notice all homogeneous systems are consistent. How do we know that? Just by looking at this. Well, it's because there's always the trivial solution. Okay, so because the solution basically is 0, 0, all zeros is always a solution. All right, so this ordered tuple of all zeros is always a solution. Right, so you can kind of look at this. So for example, 0, 0, x equals 0, y equals 0, the ordered pair 0, 0 is going to be a solution to this equation and also to this equation. In the case of this system here, the ordered triple 0, 0, 0 will solve all three of these equations at the same time. These are called trivial solutions, right? Just simply because they're not interesting. Other solutions that are not all zero are called non-trivial. These are the trivial solutions. All homogeneous systems have at least a trivial solution. Okay. All right. Very good. Very good. And let's crank out another theorem here. Okay. So the next theorem says basically that if the reduced row echelon form of an augmented matrix for a homogeneous system in n variables has fewer than n non-zero pivot entries, then the system has a non-trivial solution. Basically, this theorem is going to describe when a homogeneous system has a non-trivial solution. Okay, so let's talk this through. Let's write the theorem out. So if the reduced row echelon form augmented matrix for a homogeneous system in n variables has fewer than n pivot entries, then that system is going to have a non-trivial solution. Okay, so for example, something like this. Let's see here. So let's say I have the following two systems. I'm just going to dump them straight into the augmented matrix. But let's say I have a system that looks like this: 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. Right? Something like this. This matrix has n variables, and each of them has a pivot entry, right? So n variables, 3 in this case, and all 3 of them have pivot entries. They have non-zero pivot entries, right? So this has only the trivial solution. Right? In fact, you can just read it off, right? You can see that that's obvious, right? x3 has to equal 0, x2 has to equal 0, x1 has to equal 0. Right? Here's another example. What about this? 1, 0, negative 3 halves, 0, and 0, 1, negative 1 half, 0, and then 0, 0, 0, 0. This is also a matrix with 3 variables, a system with 3 variables, x1, x2, x3. But here you can see that I do not have a pivot entry for the x3 variable, right? I just have a 0 here. There's no non-zero value, so there's no pivot entry, right? So this has a non-trivial solution. This it's going to have a non-trivial solution. In fact, this one will have infinitely many non-trivial solutions. Right? It's got a independent variable, right? That x3 is independent. Okay. Okay. Very good. So this is what this theorem is describing. Okay. And this is only true for homogeneous systems, systems where the scalar vector, or sorry, the scalar matrix is all zeros. Right? Systems where this whole section here is 0, 0, 0, 0, 0, 0, 0. Right, so this theorem only applies to homogeneous systems. It's very important. This does not apply to non-homogeneous systems. If you have scalars over here, then you have the potential for, it doesn't apply. Okay. What happens if we have a system that has fewer equations than it does variables? Okay, so if a system has fewer equations than it does variables, what happens to homogeneous systems that have fewer equations than variables? Okay, I feel you may be sensing that this is going to imply something about those kinds of systems. So things that look like this. Here's an example. Let's say 1, -3, 2, -4, 8, 17, 0. So kind of a big system. So 3, -9, 6, -12, 24, 49. Homogeneous though, right? So remember, this is my augmented matrix over here. -2, 6, -5, 11, -18, -40, 0. So here's a system with 3 equations, but 1, 2, 3, 4, 5, 6 unknowns. Okay, and so something like this, you could go through the work of putting this into reduced row echelon form, but what you get is 1, -3, 0, 2, 4, 0, 0, and then 0, 0, 1, -3, 2, 0, 0, and then 0, 0, 0. Okay, everything is a 0 except for this guy down here. Okay, so if you went through the process of doing the reduced row echelon form, right, the Gauss-Jordan elimination stuff, you would get it into this form. Now notice you've got your pivots here, here, and here, right? And so you've got independent variables, 3 of them. Okay, so this matrix is going to have non-trivial solutions because of these non-pivot columns. Right, so in general, if you have a homogeneous system with fewer equations than variables, so you have more columns than rows, then it's definitely going to have a non-trivial solution. Right, so to kind of answer this question, homogeneous systems with more variables than equations will always have non-trivial solutions. Okay. Very good. All right. Okay, so that's so we're kind of introducing the idea of a homogeneous system. We'll come back to these; they'll be important later on as well. We've talked about the Gauss-Jordan reduction, and we've defined what we mean by that, and then also we've discussed how Gauss-Jordan reduction results in a matrix that has a particular form, and that form is called the reduced row echelon form. So we talked about those 3 items so far. Now, the last thing to talk about here is just a simple kind of interesting phenomenon that you may or may not have already gleaned from doing some of these examples. But basically, let's talk this through in the context of an example. So solve the two systems below. Okay, and I'm just going to put them straight into matrix form. So 3, 1, negative 2, 1, 4, 0, negative 1, 7, 2, negative 3, 5, 18. Right, so here's the first system. And the second system is going to be 3, 1, negative 2, 8, 4, 0, negative 1, negative 1, 2, negative 3, 5, negative 32. Okay, so second two systems here. Now they're distinct systems, but if you look at these, you will recognize that actually the coefficient matrix is the same. So they're equal. They have the same coefficient matrix, but the scalars are different. Okay, so they've got different scalar matrices, but the coefficient matrix are identical for these two. Now, they do, because they have the same matrix, we can kind of take a shortcut in solving these two, right? So it would totally be possible to do the row reduction on this one, get it down into RREF, and identify the solution, and then separately come over and do the same thing here, right? To find a separate solution over here, right? Different system. But because the coefficient matrices are the same, if you think about it, all you're trying to do with Gauss-Jordan elimination is you're trying to identify pivots in the coefficient matrix mainly, right? And so all of the operations that you do over here would be the same as the operations you'd want to do over here, right? Because you're trying to, again, convert this coefficient matrix into this particular form, right? And so what you can do is you can kind of do them at the same time. You can actually solve both of these systems at the same time, right? Because of the fact that the coefficient matrices are the same. So let's talk through what that means. Right, all it really means is write the augmented matrix slightly differently, right? So you've got your coefficient matrix here, and it's the same for both of them, right? It looks like this. Okay, and then you've got this kind of divider here. And then over here is where your scalar matrix would go, right? The B in the AX equals B equation. Right? And so one of them looks like this, 1, 7, 18. And the other one was 8, negative 1, negative 32. I can just put it right next to this. Right? It's the same coefficient matrix, and now I've got two separate columns, each referring to the distinct system. Right? So this was system 1, this one is system 2. Now, keep in mind that columns don't interact with one another during row operations. They're just kind of along for the ride, aren't they? So whatever's being done over here is just kind of like impacting these guys independently, right? And so the fact that I put them next to each other doesn't do anything. And indeed, when I run through the row operations, and you can confirm this by just, again, putting this into reduced row echelon form, what you'll find is that you get a matrix that looks like this: 1, 0, 0, 0, 1, 0, 0, 0, 1 for the coefficient matrix. And then this guy, 1, 7, 18, gets converted into 2, negative 3, 1. And this other coefficient matrix gets converted into negative 1, 5, negative 3. Okay? And so you could accomplish this by just doing one set of row operations rather than doing multiple sets. Okay, and you could read the solutions directly off of this. So for the first system, the solution is x1 equals 2, x2 equals negative 3, x3 equals 1, right? Just reading it off of this column. For the second, well, it's the next column. x1 is equal to negative 1, x2 is equal to 5, and x3 is equal to -3, right? Again, just reading it off of the column. All right. Very good. Okay, and so that's just kind of a quick addressing something that people probably have already thought of when they were looking at these, perhaps. So just formally addressing that you can indeed combine the systems, but particularly if the coefficient matrix is the same. Okay. All right, and I think that's a good place to end off this section. Next time we'll get into describing equivalent systems. We'll also define the term rank and describe what we mean by row space. So we'll get into that next time. We'll leave it here for now. Everybody take care, and we'll talk to you all next time.